All right, so here we're going to talk about the reactivity of the carboxylic acids and carboxylic acid derivatives. One of the main types of reactions that these do is react with nucleophiles and do a substitution in two steps, nucleophilic addition and then uh, elimination of a leaving group. And the reactivity is a little bit similar to looking at aldehydes and ketones, but there's some key differences in how the mechanisms go, which change how the reactions work. So we're going to look at acyl chlorides, acyl halides in general are going to work similarly, anhydrides, esters, which react similar to acids, and amides. So in order to frame what we're talking about, the mechanism is important here. So if we're doing a reaction at the carbonyl carbon in all of these cases, then the strength of the nucleophile is going to be important. A stronger nucleophile is going to favor these reactions, but also the strength of the charge on the carbon, right? So the more positive that carbon is, the more favorable it is to react, right? In all cases, we have a double bonded oxygen reacting. And the other piece is after the addition, instead of proton transfer, we can eliminate a leaving group, right? So the stability here can help determine how favorable the reaction goes. So nucleophile strength is important, electrophile strength, and the leaving group ability for all phases of this reaction is going to help determine how things go. As you can see, there's different pieces bonded to a carbonyl carbon for all of these functional groups. So they'll react similarly, but their chemistry is going to be a little different. So they're going to behave a little different. So looking at the acyl chlorides, these are in order of how reactive they are as well. Right? So in general, the most reactive is the chloride, followed by anhydride. Esters and carboxylic acids are pretty similar. There's some differences there in that the carboxylic acid has a proton that it can donate. And then amides are the least reactive. We'll get to those last. So the acyl chlorides, you have more electronegative chlorine here. So unlike aldehydes and ketones, which had a fairly neutral group attached around the carbonyl, here we have a strong inductive withdrawing group attached. So that's going to pull electrons away. That's going to make this carbon relatively strong and relatively positive. As with talking about reactions of benzene, I do have lone pairs on chlorine. It can potentially do resonance electron donation, but so let's draw the resonance structure. Right, so if we share this lone pair to make a double bond, push the electrons up, this would be the resonance structure we'd make here. And it's a particularly poor resonance structure for the same reason why I couldn't donate electrons very well to a benzene ring, and that is the overlap between the orbitals between carbon and chlorine is not so good for making this pi bond here. Right, so you have weak resonance there. So it doesn't really help donate much. So it's good at pulling electrons away, bad at donating. So overall, it's going to withdraw electrons. So that's going to make it more reactive. The other piece you have to consider in these reactions is when the group comes off in the end, you make Cl minus, which is a relatively stable leaving group. Anhydride, so you've got two reactive groups here. If it's symmetrical, it doesn't really matter what we're looking at here. But our potential leaving group for this reaction, if something adds to this carbonyl, pushes electrons up, breaks it off, our potential leaving group is resonance stabilized. So that's going to be relatively favorable. You have electronegative oxygen here. You also have the chance to do resonance, which is going to be a little bit better. of a resonance contributor than we had for the chlorine. So although they look the same, since oxygen is around the same size as the carbon atom it can double bond to, it makes a stronger double bond there. So it's a stronger resonance contributor than with the acyl halides. So overall you have more resonance and then a stable leaving group, leading you to a pretty reactive molecule. So that both acyl chlorides and anhydrides react pretty quickly with weak nucleophiles like water. So they react pretty well. The esters and acids are a lot more stable. So you'll notice the biggest difference between anhydride and ester is we don't have this extra carbonyl there anymore. So our leaving group is, for an ester, a really strong base. It's a bad leaving group, a really reactive molecule. Same thing for an acid. Leaving group would be hydroxide, right? So these are going to be poor leaving groups. Which is probably going to mean, in general, we're going to need stronger reactants or something to activate them to make them better leaving groups. As should be a notable theme from organic chemistry is, well, we can use proton transfers and things like that to make what would normally be a bad leaving group a better leaving group. So in terms of its resonance structure and stability, it's going to be pretty similar to the anhydride above it. Right, so it can donate electrons through resonance, so that's going to mean that it's, again, less reactive than the acyl chloride, which is good at pulling electrons away and making a nice positive charge here, but bad at sharing and has a good leaving group. Here we have a poor leaving group, okay resonance. Right, so a lot going on here. The amide, we finally start to see some differences. We don't have an oxygen there, we have a nitrogen. And its resonance structure would put a positive charge on the nitrogen. So chlorine and oxygen, they are around the same electronegativity. Nitrogen is lower, right? All right, so if nitrogen is less electronegative than oxygen, then it's better at holding on to a positive charge, right? So the positive charge, the less electronegative atoms tend to do better as cations, as positive charge. Right, and so the more stable this resonance structure is, the more likely it is to contribute, right? We can draw whatever we want. We can draw these double bonds all over the place, but without the context of knowing that, this is a really bad resonance contributor, this is okay, this is even better, right? So more stable than the others, right? So that means that nitrogen is going to donate more electrons by resonance than the oxygen. Right? And so if we're donating those electrons in, right, that's going to weaken the partial positive around that carbon. That's going to slow down reactions of amides. Amides are pretty stable. They're used a lot in biological structures, and their stability is helpful there, right? We don't want all of our important biological bits and pieces to just fall apart. As far as leaving groups, we're trending to worse and worse and worse. Right, so whereas nitrogen, a little bit better at forming positive charge ions, not so good at negative charge ions. This is a really, really strong base. As such, it's almost impossible to make. So our chemistry depends on a couple things, right? So nucleophile strength, of course, right? We're not looking at that here. If we're looking at just the structures we're reacting with, is how positive is this carbon, right? Do we have an electronegative atom pulling electrons away? We do in each case, right? Do we have some resonance stability there? And so as we're going down and then over to amides, it's getting more resonance stability, weakening that partial positive there. Because the more electrons you dump into a double bond here, the less positive that atom's going to be, the less reactive it's going to be. So this is what we're looking at in terms of why some of these are more reactive than others.